We've spent a few lessons now talking about linear equations and inequalities. These equations are of the form y equals mx plus b, so they include what we call a linear term, that's the mx term, where the x is raised to the first power, and they also include a constant term, the letter we normally call b. What I want us to do now is to consider functions where we include another term. We call it the quadratic term, and that's a term where the power on x is 2. These new functions will be of the form f of x equals ax squared plus bx plus c, where a, b, and c are just some real numbers. So, for example, we might think of f of x equals x squared plus 5x plus 4, or g of x equals 3x squared minus 8x plus 2. These are called quadratic functions. The term quadratic comes from a Latin word, quadrare, which means to make square. And we sometimes refer to x to the power of 2 as x squared. We're actually going to spend several lessons talking about quadratic functions. We're going to talk about their graphs and look at what they appear to be visually, and we'll also solve equations that involve quadratic functions. In fact, we'll spend several lessons just on solving those equations using a variety of different tools. In this lesson, I want to spend time introducing you to the main ideas, the main terms, and the basic ideas behind the visual part, the graphing part of these functions. So for the next several minutes, let's talk about some of these graphical aspects of quadratic functions. First off, the graph of a quadratic function has a special name. It's called a parabola. And here are the graphs of two particular quadratic functions. F of x equals x squared plus 3, and g of x equals negative x squared plus 4x minus 1. Now let me ask you a few questions. First of all, what kinds of similarities do you see between these two graphs? And secondly, what sorts of differences do you see? Well, one of the first things you might notice is that both graphs are U-shaped. This is very different from the graph of a linear function, where the graph was just a straight line. We spent several lessons talking about those already. Thanks to this U-shape, we see that both ends of each of the graphs go in the same direction. They either both go up or they both go down. This is again very different from the graph of a line, where in general, one end goes up while the other end goes down. So these graphs of parabolas are already very different from graphs of lines, where both ends now are going to either go up or they're both going to go down. And of course, we have some curvature now to the graphs, whereas with the lines, everything was straight. Now, what else do you notice about these two graphs? Well, one of them crosses the x-axis twice, and the other misses the x-axis altogether. This is again very different from the graphs of lines, where typically there's an x-intercept, except in the case of a horizontal line. And in fact, there's only one x-intercept when you're drawing a line. Now, in the case of parabolas, or the graphs of quadratic functions, you might have two different x-intercepts, okay? In fact, you might have two of them. You might actually just have one x-intercept with a parabola, where the parabola basically sort of sits on the x-axis. And of course, you might have the parabola miss the x-axis altogether, as we just saw. So, for example, if you saw the graph of f of x equals the quantity x minus 3 whole thing squared, you would notice a parabola that just sits right on the x-axis at the value x equals 3. And that parabola has exactly just one x-intercept. So we've seen examples of parabolas with 0 x-intercepts, 1 x-intercept, and 2 x-intercepts. Could there be more than 2 x-intercepts? Well, if you believe me that the shape of these things is a U, then the answer has to be no, Because if the shape is a U, and it really is, then the ends of the graphs are never going to come back down again to reach to the x-axis. Or if the parabola was going down in the first place, then those ends are never going to come back up and hit the x-axis again. So that graph is not going to wrap back on itself, and you're not going to get any more x-intercepts. Now, thanks to this distinctive U shape, there's a very special point on the graph of every parabola. And this is another bit of terminology that we need to make sure we put in our memory bank. It's either the lowest point on the graph when the ends of the graph both go up, or it's the highest point on the graph when both ends of the graph go down. And that special point is called the vertex of the parabola. In a future lesson, we're going to talk about ways to actually calculate the coordinates of the vertex of a parabola. But just let me point out that in the two graphs that I already showed you, the vertex is 0, 3 in the first graph and 2, 3 in the second. Now don't worry, I promise to show you how I actually find those 2 points in an upcoming lecture. But just remember, the lowest point or the highest point on a parabola has a special name, and it's called a vertex. Now, we really should ask, and you really should ask, why is it that the graph of a quadratic function is shaped like a U? I mean, couldn't it have been shaped in some other way? And what's telling us whether the ends go up or whether the ends go down? It turns out that the answer is pretty simple to that question. It's the sign of the coefficient in front of the x squared term. That's the only thing that determines whether the ends go up or the ends go down. When that sign of the number in front of the x squared is positive, as it is in the case of f of x equals x squared plus 3, then the ends go up. Now let's pause there for just a second. F of x equals x squared plus 3. What's the number in front of the x squared term? You might be saying to me, I don't see a number in front of the x squared term at all. But remember, there's a 1 hiding in front of that x squared term. We don't typically write it there explicitly, but there really is a 1 in front of that x squared term. So that 1 is positive, and that's why the ends of the graph of x squared plus 3 go up. When the sign in front of the x squared term is negative, as it is in the case of g of x equals negative x squared plus 4x minus 1, then the ends will always go down. And there's nothing else that impacts the upwards or downward shape of these parabolas, only the sign of the number in front of the x squared term. So that's a very quick way to critically think about what your graphs are going to look like. As soon as you look at that x squared term, you look at the number in front of it, it will immediately tell you whether the ends will go up or the ends will go down. Now, you might be asking, wait, can a parabola be drawn so that it's actually sitting on its side? In other words, could the parabola sort of have the ends going out in one direction, maybe both to the right, for example? Something like this graph. Well, one way to answer that question is yes, because that graph really is a parabola. Okay, so I could say yes to that question, but another way to answer it is no, and I'm going to say no if you only want to deal with graphs of functions. Several lessons ago, I talked with you about graphs of functions and something called the vertical line test. You remember what the vertical line test says? It says that if a vertical line can be drawn that crosses a graph in at least 2 different places, then that graph cannot be the graph of a function. Well, if you take a parabola where both ends open to the right rather than up or down, you can obviously draw a vertical line which crosses the graph in at least 2 places. Take, for example, the line x equals 2. So we see that although this sideways U is a parabola, and it really is, it's not the graph of a quadratic function. And that's a small but important distinction to make. And because this sideways parabola, if you want to call it that, is not the graph of a function, we will not spend any time talking about these kinds of parabolas in this course. Okay, to close out these general comments on the visual side or the graphical side of quadratic functions, I'd like to show you a few examples of how to draw the graph of some different quadratic functions. They'll all be parabolas, but the question is, if I give you the function, I just give you the rule for the function, can you figure out where to put the graph? That's the thing we want to try to learn as we walk through the rest of this lesson. So let's look at several of these together in the rest of this lesson. First of all, let's sketch the graph of f of x equals x squared. That's the most basic parabola I could probably hand us, but it turns out you and I have already seen this one. So maybe you're saying, what a waste of time. Well, let's walk through this together, and if nothing else, convince ourselves of why the shape really is a U, and why in this case the U is pointed upwards. All right? Remember that if you're just completely lost when you want to graph a function, one thing you can do is plug in some different x values into the function and see what the y values look like. At that point, you would then have the coordinates of several points, and you could plot those points on a piece of graph paper and connect the dots. So let's find several points on this parabola that's related to f of x equals x squared. I'm going to plug in x equals 0, 1, 2, and 3, and I'm just going to see what values we get as output values to the function. So f of 0 is 0 squared, which of course is 0 times 0, which is 0. Lots of zeros there. And that means that the point 0, 0 is on this graph. 0 for x, 0 for y. Let's plug in 1. f of 1 is 1 squared, which is 1. And so the point 1, 1 is also on the graph. Now let's try something different. f of 2. f of 2 is 2 squared, which is 2 times 2, which is 4. And that means that the point 2, 4 is on the graph. And lastly, f of 3 would be 3 squared, which is 9. So the point 3, 9 would also be on the graph. Now, if you pulled out a piece of graph paper and you just plotted those points, you would have the start of the graph. In fact, if you did that, you would start to see sort of 1/2 of the U shape taking shape as you draw that graph. But we really ought to plug in some different numbers as well, because I only plugged in 0 and some positive values there. But remember the domain of this function. We talked about domains a few lessons ago. The domain of this function is all real numbers. I can plug in any real number that I want, and in particular, I can plug in some negative numbers as well. So now I'd like to try plugging in things like -1, -2, and -3, and let's see what we get as the output values there. So f of -1 would be -1 squared. Now think of -1 squared as -1 times -1. And if you look at the two negatives, they will cancel one another, and the final version of the output will be +1. So that means that the point -1, +1 is also on this graph. So when you go to plot that on your set of axes, you're going to go 1 to the left for the -1 for x, and 1 up for the 1 for the y coordinate. And that will also be a point on your graph. Let's try plugging in -2 for a moment. f of -2 would be -2 squared, which is -2 times -2. And again, those two negatives will cancel and give you +4. So the point -2, 4 is on the graph. And lastly, f of -3 would be -3 squared, which is -3 times -3, which is +9. Now, that gives you, what we just did with all those calculations, gives you 7 different points to plot for the graph of y equals x squared. And if you plot those carefully on a piece of graph paper, it should be pretty easy to see that what's coming out is this nice U shape that we talked about before. And I want you to notice as we close out this plotting of points for f of x equals x squared, how important it is to know when you raise negative numbers to powers whether the negative signs are going to cancel or not. Now, let me also quickly point out that the domain of this function, as I said a moment ago, is a set of all real numbers. But what is the range of the function? Remember, the range of the function is the set of y values that's going to come out once you've plugged in all possible values for x. In this case, the range of this function is actually from the y value 0 up to the y, let's say, plus infinity. Plus infinity is not a real number, but by saying that the range is from 0 to plus infinity, we're saying that starting at 0 for y, we will get every other possible y value from 0 and above. And we can see this from the graph where the vertex of this parabola is right at the origin 0, 0, and then the rest of the graph goes up. Okay, let's use some of the graphing tricks that we learned in a previous lesson to see how we might draw the graphs of some other quadratic functions now that we can see what the graph of x squared looks like. So let's move on to this example. Sketch the graph of g of x equals x squared plus 3. Now, remember, one of the graphing tricks or rules that we saw a few lessons ago is how we can change the graph of one function to get another, where all we do is add a constant to the original function. In this case, x squared plus 3 could be thought of as starting with x squared, which we just plotted a moment ago, and adding 3 to it. Do you remember what happens when you do this sort of thing, where you just add 3? What happens to the graph? Well, the graph gets moved, and it gets moved upwards 3 units. So to draw the graph of g of x equals x squared plus 3, we simply start with the graph of f of x equals x squared that we just drew, and we shift it 3 units up. And when I do that, it gives me a graph that looks something like this. In fact, you might remember that I showed you that graph closer to the beginning of this lesson. And notice that the domain of this function is still the set of real numbers, which you can write as the interval from minus infinity to infinity. But notice now that the range of this function g of x has changed compared to the range of f of x. Now, the lowest y value that you're going to get is 3. That's where that vertex is located. And then the rest of the graph goes up. So the range of this new function is actually the interval from 3 to infinity. And the vertex, it's at the point 0, 3. I can read that right off the graph. Okay, let's try another example. Let's sketch the graph of h of x equals x minus 2 whole thing squared. By the way, please don't be thrown off by the fact that I'm changing the names of the functions. We had an f of x and a g of x and now an h of x. I'm just trying to give them different names so we can keep track of them. There's nothing special about those names. I'm just trying to give them different ones. Now, notice that this function looks very different from x squared, and it also looks different from x squared plus 3, the one we just studied a moment ago. Now what I'm doing is I'm changing the x to x minus 2 in the x squared function. I'm not adding or subtracting 2 to the whole function. I've actually gone into the x part of x squared and replaced that x with x minus 2. Now here's my question for you. From the graphing tricks we saw a few lessons ago, what does changing the x to x minus 2 do to the graph? Well, it doesn't move it up or down like in the previous example. It's going to shift it either left or right. So here's the trick question of the day. Which is it? Does x minus 2 squared shift the graph of x squared to the left, or does it shift it to the right? Well, the answer is that x minus 2 squared's graph is exactly the graph of x squared shifted to the right 2 units. We don't go up or down at all with the shift. We simply shift to the right 2 units. So if you start at x squared and draw its graph, the vertex going right through the origin, and shift it 2 units to the right, you'll have the graph of h of x equals x minus 2 squared. Now here's a question. Where's the vertex of that new graph? Well, just look at the graph itself. It's now at the point 2, 0. And notice that we're still shaped upwards. The legs of the graph, if you will, the ends of the graph, haven't flipped down. They're staying upwards, just like the graph of x squared was as well. And one last question. The domain and range of this new function, well, I can still plug in anything I want. So the domain is still minus infinity to infinity, and the range of this new function is the interval from 0 to infinity, including the 0. Okay, let's look at some more examples of graphs of parabolas, which are a bit more complicated. I really want to make sure that we push the envelope a bit on these. I've shown you 3 graphs now, but there are a few more I'd like you to see. Stay with me. We're going to walk through these step by step. They are a bit more complicated, but once you see how to put together these graphing tricks, you'll actually find that you can graph just about any quadratic function that someone hands you. So here's the next example I want us to sketch. Let's sketch the graph of j of x equals the quantity x plus 1 raised to the second power minus 4. Now, to do this, I need you to see that what we did was we started with the function x squared, and we actually did 2 things to it to change it into the graph that we want to talk about now. First, and I mean this sincerely, first we changed the x to x plus 1. Now, what is changing the x to the x plus 1 going to do to the graph? Well, it will move the graph of x squared over 1 unit. Which direction? That's right, it's going to move it to the left. Okay? Now, you might say to me, hold on, wouldn't plus 1 move it to the right? The answer is no. And probably the best way for you to understand that we're going to go to the left is to think of x plus 1 as x minus a negative 1, right? X plus 1 is the same as x minus a negative 1. And now do you see that negative 1 that's sticking out there? That should remind you to go to the left. So by switching from x squared to x plus 1 squared, we're going to take the graph of x squared and move it to the left 1 unit, right along the x-axis. Okay? That was the first thing we did. But wait a minute, we also subtracted a 4. Do you remember that? And we subtracted that 4 not from the x part, but from the whole function. Now, what does that subtracting of the 4 do to our graph? Well, when you subtract 4 from the whole function, you then have to move your graph down 4 units. And so now I see what I have to do to graph j of x, this new function. I have to do 2 things step by step. First, I start with that graph of x squared with its vertex right at the origin. I move it 1 unit to the left. That's the first change that I make. And then I move that down 4 more units. The new graph then will have the same sort of shape as the x squared. Its ends will still be going up, but now the vertex is at a totally new point. Can you see what that point is? It's actually -1, -4. So I've just translated the graph of x squared down to a new vertex, but the rest of the shape of it is still exactly the same. Now, let me talk about a few more of these kinds of different graphs by talking about this following example. This one has a bit of a change to it, so follow me closely as we do this example. Sketch the graph of, let's call it k of x. I guess I'm on a real name-changing crusade today. Sketch the graph of k of x equals minus x squared plus 1. Okay? Now, to start this example, let's make sure we understand what this function is saying and what it's not saying. I think this is very important. It's important for you to note that this function is not the following: negative x being squared plus 1. Do you see how the minus sign in what I just said is inside the parentheses of that function? And if that's where the minus sign was, the exponent 2 would just cancel it out. But in my function k of x, the minus sign is actually sitting outside of the squaring of the x. Let me say it this way. I could write k of x as the negative of parentheses x squared plus 1. And that's very different from negative x squared plus 1. You see how that minus sign would be sitting outside now the x squared term when I write down k of x. That's very important for you to see. And it means that the minus sign in k of x is not being canceled in any way by that exponent of 2. Okay, we've had that little conversation. Now let's get to the graph of this function. Well, I want to think again about how to take the graph of x squared, that's our good friend who goes through the origin, vertex at the origin, and then goes up. I want to think about that graph, and I want to think about changing it in 2 steps again to get the graph of negative x squared plus 1. Okay, here are the 2 steps we're going to take. First, we start with the x squared and we multiply by a negative 1. Now, do you remember from our bag of graphing tricks what multiplying by a negative 1 with the whole function is going to do to the graph? Multiplying by a negative 1 is going to take the graph and flip it across the x-axis. So, when I start with x squared and I multiply that by a negative 1, I'll have the graph of negative x squared, which is exactly the same parabola with the vertex at the same place, but it's now been flipped upside down, if you want to think of it that way. So, I go from x squared to minus x squared by flipping. When I then add that 1 to the whole function, what does that do? Well, adding a 1 to the whole function makes the graph go up 1 unit. So, in a nutshell, to get to the graph of negative x squared plus 1, I'm going to start with the graph of x squared. I'm going to flip it across the x-axis so that it's now upside down, if you want to think of it that way. And then I'm going to shift that graph up 1 unit. And once I've done those 2 steps in that order, the graph will then look something like this, where the legs now, or the ends of the graph, are now going down. Now, I want you to think about domain and range for this function. What is the domain of negative x squared plus 1? Well, I'm allowed to plug anything in still that I want in for x, so the domain is still the interval from minus infinity to infinity. But look at the range now. Where will the values of this function go in the y direction? Well, the lowest they go, if you want to think of it this way, is negative infinity. In other words, I'm just saying that they go on forever in the negative direction. But what's the highest that they're going to get as a y value? Well, the highest that any y value will be for that function is going to be 1, because that's where that vertex is located, at 0, 1. So the range of this function is the interval minus infinity to plus 1, and the plus 1 has a bracket next to it to indicate to me that I can include that 1. Now, you might be wondering, where's all the algebra here? Why aren't we playing with equations? What's all this graphing stuff about? Well, I have to be honest with you. We need to understand these graphs. If all you do in algebra is spend lots of time just manipulating equations and you don't think about the visual side of it, I think we miss out on some very important aspects of algebra. So I hope you'll be patient with me as we walk through these kinds of visual or graphical techniques, but it's extremely important that we do so. In fact, let me try to tie the graphical and the algebraic together as we finish up this lesson. In the graph I just showed you, is it easy to see the x-intercepts? Remember, those are going to be the points where the graph crosses the x-axis. Well, if you were careful about drawing it, it would look like that the x-intercepts are at negative 1, 0 and 1, 0. But here's a question for you. How would you know it for sure? Maybe you drew the parabola too wide or maybe too thin. Well, to find those x-intercepts, which is an important, very important thing to do with a function, you could go back to the algebra, not to the picture, and set the whole function equal to 0 and solve for x. You see how I'm now connecting x-intercepts, which is a graphical question, with some algebra, which involves manipulating an equation. So, here we go. To find those x-intercepts, I'm simply going to take the function, negative x squared plus 1, and I'm going to set it equal to 0. And now, I'm looking at an equation. Why don't we see if we could actually solve that, okay? Then I would be able to connect the graphical to the algebraic. Well, honestly, if you've been following along, you should have a pretty good idea by now what the graph of a parabola looks like just by examining the quadratic equation. So I'm going to move away from that x-intercept question, and we'll solve that later on in another lesson. But to close out this lesson, I want us to take a quick quiz. So here's the quiz, and then we'll go ahead and be done. I want you to match the equations below with their graphs. So I'm going to give you 4 equations to close out the lesson, and you're going to self-quiz to see if you can match those equations with their graphs. Here we go. We're going to have f of x equals x squared minus 2, f of x equals negative x squared plus 2, f of x equals x minus 2 whole thing squared, and f of x equals x plus 2 whole thing squared. All right, there's 4 graphs now. Which ones are they going to match up with? Well, I think I can do x minus 2 squared, x minus 2 whole thing squared pretty quickly. That's going to be the graph of x squared shifted 2 units to the right. So if I can find that graph, I'll have the graph of x minus 2 whole thing squared. Now I've got x plus 2 whole thing squared. What does that do? That shifts the graph of x squared to the left. So if I can find that one, I'm done. Now let's look at negative x squared plus 2. Notice that has a negative sign in front of the x squared. What does that mean? It means that the legs of the graph have to be going down. And I'm guessing there's only one such graph in the list. And so that one has to match up. And lastly, x squared minus 2 is going to be the graph of x squared shifted down 2 units. Did you get those answers? I hope so. Hopefully that self-quiz would help you as we finish up today. In our next lesson, I'm going to go back to the algebra. We're going to go back to the equations, if you want to think of it that way. And we're going to solve some equations, and we're going to do so using factoring. I'll see you then.